Hey everyone, this is the second part of the video concerning lysergic acid diethylamide. We were discussing the use of lysergic acid coupled with diethylamine, which basically is the final step in the synthesis of lysergic acid diethylamide. So, in general, this can be done in many ways. Peptide coupling reactions are tricky, or were tricky, because the hydroxyl group on a carboxylic acid is not a good leaving group. So on an acyl chloride, you've got the chloride, that's the leaving group. On an anhydride, you've got another conjugate base of an acid coming out. So basically what's done is the carboxylic acid must be activated in some way or another. There are several reagents out there. The initial syntheses used some strange hydrazine intermediate or some azide. That was the very first sort of prototypical synthesis. But later on they found that there are reagents that can be used that will not destroy the lysergic acid molecule, such as phosphorus oxychloride. Phosphorus oxychloride is a reactive molecule. I believe it forms the anhydride, mixed anhydride with lysergic acid. So when it does that, what you have is basically an excellent leaving group. There's a nucleophilic attack by the amine, which is diethylamine. So basically that's just how it works. That yields lysergic acid diethylamide. The POCl3 method is pretty commonplace. It's probably one of the more referenced ones. So recently there's been some new reagents developed for peptide synthesis, which is basically just synthesizing proteins, sometimes in solution phase, but mostly on solid phase. So peptide coupling reagents, what are they? Peptide coupling reagents, and by the way, I'm talking about these because this is the way I think it's the future of lysergic acid diethylamide synthesis because of these coupling reagents that have come out. Because they're pretty cheap, they're getting cheaper, and you don't need much. The conditions are pretty mild, it probably won't destroy your product. So with peptide coupling reagents, you can have several different ways of doing so, doing the coupling reaction. Some people might talk about PIBOP and other reagents. I'm only going to talk about DCC and DIC, the carbodiamide reagents, and the uranium reagents. But they both basically do the same thing. But let's start with DCC and DIC. So DIC is a liquid. It's a fairly toxic liquid. Basically, there's a carbon in the center. There's a central carbon, and there are two double-bonded nitrogens. Now, this makes that carbon very electrophilic. So, basically what happens is an ester forms with deprotonated carboxylic acid. Now, in most cases, to prevent racemization, which is important in lysergic acid diethylamide synthesis because stereochemistry is key, in most cases, some HOBT is added for hydroxybenzotriazole. This kind of acts as a transfer for the carboxylic acid ester, or it's basically an ester, and it's activated form of the carboxylic acid. And from there, there's a nucleophilic attack by the diethylamine or the amine, whatever you're using. DIC is a liquid. It's more commonly used in solid phase synthesis because the byproduct of this synthesis is soluble, and basically what you can do is just wash out all the unwanted products through the resin. DCC is used more in solution phase synthesis, which is what you would do with lysergic acid diethylamide. Basically, DCC produces a very insoluble product, as well as your desired product. And this insoluble product can be filtered right out, and your lysergic acid diethylamide or whatever peptide you're trying to make will end up in the reaction mixture, the filtrate. So another set of coupling reagents are the uranium coupling reagents. There's TNTU, HATU, HBTU, all of these different variations. But they all do the same thing. They form this ester with the carboxylic acid that's been deprotonated. And this ester is activated. It's basically the activated form of that carboxylic acid, and it is vulnerable to nucleophilic attack by diethylamide. So basically that's it for coupling reagent, and that's pretty much it for the synthesis. The main difficulty is usually in the workup and solubilizing the product and making sure the product doesn't degrade. So it may sound easy from just these two steps, but the most difficulty is in running columns, using the right solvents to purify your LSD, stuff like that. So that's pretty much it. Usually LSD is dissolved in ethanol or ethanol water when it's found in a liquid form. But that's pretty much it for the synthesis. I haven't gone in depth into a whole lot, but most of it's out there. There's a lot of information on the synthesis of lysergic acid diethylamide. Alright, so now on to pharmacology. Okay, now here's where the interesting part comes. Well, actually I find this synthesis quite interesting too, but this pharmacological aspect is strange because it turns out that lysergic acid diethylamide is not that great of a ligand for the serotonin 2A receptor, which is responsible for all psychedelic activity, whether it's psilocin or mescaline or LSD. Basically, LSD is so potent, the doses are in the microgram range. Not the milligram range, as is with other compounds like DOI or DOC. DOI is kind of sub-milligram, but DOC probably. So, it's remarkably potent, but the science shows that it's actually not that great of a ligand. Yet, it still produces very potent effects. Anyone who's tried LSD will agree that the effects are quite intense. So, what's the reasoning behind this? Now, for a long time, the serotonin 2A receptor was just seen as a one-pathway receptor. It was, I believe, the first model for the serotonin 2A receptor involved only hydrolysis via phospholipase C. So, phospholipase C, what it does is it takes an element of the plasma membrane and breaks it down into inositol and fatty acid. And inositol is a secondary messenger inside the cell. When inositol triggers this cascade that ends up with a release of calcium ions. And calcium ions are these cations that can mediate many different things, including release of neurotransmitters. But the plot does thicken, as new research shows. It turns out that there's not only one pathway, there's a second pathway that goes through an enzyme called PLA2. Now, PLA2 is responsible for release of arachidonic acid. Arachidonic acid, it does many things, and honestly, I don't know too much about what the macroscopic effect of arachidonic acid is. But I can be sure that there's a release of arachidonic acid, and arachidonic acid is also associated with some responses after a trauma to the brain. So there's, I'm not sure what the official term is, but when there's trauma to the brain, there's this sort of response that's thought to be mediated by arachidonic acid, where there's an excitatory effect on neurons throughout the brain, and it sort of spreads out throughout the cortex. But other than that, I'm not very well versed on the arachidonic acid pathway. Dr. David Nichols did some great research on this concept called functional selectivity, which is basically just the fact that there are two different pathways, and the ligand changes the conformation of the receptor in one way that might favor one pathway over the other. And most psychedelics have different ratios of which pathway they activate. So it turns out LSD is PLA2. It mostly induces the PLA2 pathway. However, the EC50, which is the effective dose for 50% of the population, for the arachidonic acid effect is higher than that for the inositol triphosphate effect, the PLC pathway. So it's hard to know what exactly this means. However, there's a large gap in intrinsic activity when compared to serotonin, which is a full agonist. It's the model. It's seen that the intrinsic activity for the inositol triphosphate accumulation is only 22% or something like that, and it's higher with the arachidonic acid. It also turns out there are a lot of non-psychedelic compounds that bind to the serotonin 2A receptor and agonize it. Glyceride is one example. There's several examples of it. It's not really well known why they don't produce any psychedelic effects, but there is some research showing that the metabotropic glutamate receptor is involved. It forms a heterodimer with the serotonin 2A receptor. And essentially, if you knock out that metabotropic glutamate receptor, it abolishes. The psychedelic effects are pretty much abolished completely. So that's a serotonin 2A receptor. I mean, it's got a close cousin called the serotonin 2C receptor. It's actually very similar in structure, almost to the point that it's hard to distinguish ligands that bind selectively to one receptor over the other. But the serotonin 2C receptor is also involved in the psychedelic response, but not as much. It's not as important. And then there's the serotonin 1A receptor as well, which sort of is somewhat of an opposition to the serotonin 2A receptor. Not perfectly, but what it does is it hyperpolarizes the cell versus increasing excitability. It decreases excitability. So, yeah, so there's serotonin 1A receptor agonism as well, with LSD, also psilocin, I believe. Some other psychedelics have no serotonin 1A agonism effects. LSD is probably, it's a very, very promiscuous drug. It binds to many different receptors. So there's all these serotonin receptors. It binds to many, almost all of the known serotonin receptors, I believe. But it also binds some dopamine receptors. I think the D2 receptor and the D3 receptor are especially affected. There's some adrenergic receptors, which are probably more likely responsible for the somatic effects of LSD. There's some more receptors. I won't go into every single one of them, but I highly suggest some of Dr. Nichols' lectures on psychedelics, because he does go through functional selectivity, psychedelic research, and all of that stuff very well. And he's probably the foremost expert on lysergic acid diethylamide in the United States and perhaps in the world. Anyways, so there's the pharmacology. Now, pharmacology can be used to treat disorders. Now, as I mentioned in the history, LSD found a huge niche in psychiatry, and it was studied in a lot of different mental illnesses. So recently, there's been a study, probably one of the first few studies for a very long time. It just came out in 2014. It was a study on terminally ill patients in Switzerland. These patients were about to die, basically. They were so close, they were so sick that there was basically no other treatment left for them. So they gave these people who were anxious, they were anxious about their death. As one can imagine, death brings a lot of anxiety with it, sometimes a debilitating anxiety. So they were given fairly large doses of LSD, I think 200 micrograms, although there may be varying doses from session to session. And they were given this LSD, and basically there was a net improvement in their life outlook. And it's known that psychedelics can induce very long-lasting long-lasting personality changes, just like psilocybin, which is another psychedelic that's derived from magic mushrooms, aka psilocybe or paneolus mushrooms. Alright, so that's the pharmacology bit of it. It was a really quick run-through, and I really recommend reading more on it. There's a lot of literature out there describing psychedelic pharmacology. But the next part, and the next part is I cover the medical uses as well. The next part is basically my opinion. Why am I talking about lysergic acid diethylamide? And I felt like making this video mostly because I wanted to say that this compound has a lot of potential in psychiatry, and it's misrepresented way too often. I mean, we associate LSD with the hippies and everything, and possibly psychosis, you know. But it turns out that LSD could be very, very helpful in changing hard-to-treat disorders. And psilocybin's been used for treatment-resistant depression, and it works to an extent, and same for also for terminal illness anxiety. So I believe that there's way too stringent regulations on this compound right now, and there's too much politics and too much political inertia that's going into preventing the research in the United States. So basically, I mean, I think that people often have a wrong perception about lysergic acid diethylamide. Yes, it does produce, it does have psychotomimetic effects, but in reality, it's the set and setting that makes the world of difference. It's the difference between a bad trip and an extremely valuable spiritual experience. So set and setting, that's why a lot of these studies have been successful compared to accounts of recreational use of LSD. Some, because these psychotherapy sessions are done in a very comfortable environment. There's a therapist talking with whoever the patient is. There's typically a bed or something soft or comfy to lie on. This is compared to maybe how a trip might be in a bare hospital with people in lab coats poking and prodding you. I mean, that's a recipe for a bad trip. So that might explain a lot of the literature from before describing LSD as more of a psychotic agent that produces schizophrenia-like symptoms. However, there was an interesting paper, I forgot his name, I wish I knew it. He does most of his research on psilocybin. But it was some interesting research inferring that the early psychotic state, or the pre-psychotic state, is very similar to the psychedelic state. It's not identical. There are some major differences, but there's similarity. And also, in that same paper that mentioned this, it's also said that there's potential that psychedelics, so LSD, psilocybin was used as an example, could stimulate glutamate release in certain places and create stronger connections. So that might explain how some of the effects are longer lasting, because the strengthening of the synapse will last over time, although not forever, usually. Things change. Let's see what else. So anyways, I mean, that's all I have to say. I may do another video with better citations later. I just wanted to give you this brief overview of LSD. because I'm pretty bored. So until next time, this is Richard signing off.